So I'm Daan, and I want to introduce Elton Pinto here. He wrote me about a year ago that he would like to do his master's project on Perceus backend for OCaml. And I always want to help students, so I highly discourage him to do this, because it's way too much work and too ambitious. So I spent a month doing that, but Elton persisted, and now here we are, and he's going to report on what he did over the past year. He's working now for a company, but I think next year Elton will go to UPenn as a PhD student. Take it away, Elton.
Is the audio fine? Or? Okay. All right. Hi, everyone. My name is Elton, and thank you, Dan, for the introduction. And I'll be presenting Exploring Perceus for OCaml, which is part of my master's thesis that I worked on last year. I'm currently working at a venture capital, but I'll be starting my PhD next year. Cool. So in 2021, Reinking and G et al. Presented Perceus, which is a novel compiler-guided reference counting system with reuse. And one of the distinguishing features of Perceus is that it's garbage-free. So at any point during a program's execution, only live objects remain on the heap. The most well-known implementation of Perceus is in Coca, and the paper evaluates Perceus using Coca against programs written in other programming languages like OCaml, Haskell, C++. And it runs pretty good, so in terms of both execution time and memory usage. But therein lies the downfall of the evaluation. There's been no direct comparison between Perceus and other memory management schemes within the same system. So we don't know for sure how good Perceus is. So here's what we did. We implemented a prototype of Perceus in OCaml 4.14, x86 64-bit backend, and it completely replaces the garbage collector. So in all of the benchmarks we've run, the garbage collector doesn't run. Right now, we don't support exceptions in mutable references. Like it will compile, but it will leak memory. But every other feature of OCaml is supported. And we've evaluated this on the same benchmark suite as the Perceus paper, and the performance results look quite promising, so we want to keep studying this. The source code is available on GitHub, and if you want to learn more about the implementation details, you can find it in my thesis, which is linked in my website. So the rest of the talk, I'll first walk through how Perceus looks in OCaml, and then I'll talk a little bit about the changes we made in the runtime, and finally we'll get into the evaluation. Cool. So first, Perceus. So most reference counting implementations are scope-based, and they might hold on to memory for too long. So if you consider this example here, we've got, it allocates a big list, say a list containing a million elements, then performs a map operation on it, and then prints the resulting list. In scope-based reference counting systems, the drops get inserted at the end of the scope. So now, when you print the y's, x isn't alive beyond that point, but you're still holding on to both lists because the drop to x's happens after the print list. Perceus does things a little differently. So instead of reference counting being scope-based, it uses this notion of ownership in which the function takes ownership of its arguments and is responsible for invoking drop on them. So a neat consequence of this is that reference counting becomes more precise, and so you get the garbage-free property from that. So let's take a look at how map is implemented to see how Perceus inserts the reference counts. So this is a map function written in OCaml. So after running Perceus, it's going to insert RC operations as follows. So note how it drops an argument as soon as it no longer needs it. So in the cons branch, for example, x's is not used after that point, so it invokes drop on x's, but then x and xx are used, so it first dumps them and then drops the parent. So this is what Perceus would output, and while it seems all right on the surface, it isn't entirely efficient because there is a little bit of redundancy. See that? Let's inline the drop operation. So after inlining it, you'll see that if x's is unique, you perform a drop on the children and then free the parent, right? So in this case, you're dumping the children first and then invoking drop on the children, so the reference count remains the same. So can we do away with this redundancy? The answer is yes. So we push down the dumps into each of the branches, then the dumps and drops cancel out. And so what you end up with is this program. So if x's is unique, then you only invoke free and you're not performing any RC operation on the arguments, and that's the fast path. And if it's not unique, then you dump the children and decref on the parent. This whole process is referred to as drop specialization, and we've implemented both Perceus and drop specialization in the Lambda form of the OCaml compiler. So all of this works. But that's not all we can do with Perceus. Perceus also supports reuse. So in this program here, note that in the unique case, we free a node and then allocate it right after. Right? So we could potentially reuse the memory that's being freed. So Perceus does this by using a notion of reuse tokens. So instead of freeing the x's, it will return a reuse token that essentially points or tells the constructor to try and reuse memory if possible. So we modify the semantics of constructors to use the reuse token and allocate inline, or I guess assign fields in place, as opposed to allocating a new node, so you could reuse memory if possible. We haven't implemented this yet, but it's in the works, and I'll talk about it a bit more as we get to the evaluation. So now that we are familiar with Perceus, let's look at the changes we made to the runtime system. So OCaml is not reference counted, so the object header doesn't have an RC field. So we first had to bake that in. So here's how we did it. We just split the WO size field in half. WO size encodes the number of fields that an object has. So a consequence of doing this is now objects can only hold on to half as many fields. But we can still support the previous WO size by assigning a special field after the object header that encodes the actual WO size, but we haven't implemented that yet. You'll also notice that the color field is still there. We don't use it, but we haven't entirely removed it, so it's still there. Also, it's only supported on 64-bit systems as of now. Cool. So the next thing is we have to implement the primitives themselves. So here are some primitives that Perceus uses. Dup, drop, decrement is unique, allocation, and freeing. Dup and drop have specialized forms as well. So if you invoke drop, if you know that you're invoking drop on a pointer, say, then you don't need to check if the object is a pointer. So you can just directly access the ref count and decrement it. I haven't showed that here. But there are specialized forms. I talk more about it in the thesis. So one way of implementing these primitives is to write them as external C functions, because OCaml has a way to write external C functions that you can call from within OCaml. But let's try and understand what the implications of that will be. To do that, we need to understand the different calling conventions at play in OCaml. And to our knowledge, there are 3 conventions at play. The first one is the OCaml convention. So OCaml, unlike C, has a caller saved. Well, all registers in OCaml are caller saved. So a consequence of that is when you invoke a function, say f, right before going to the function, the compiler will have to spill all live registers. Now what this does is it makes exceptions fast in OCaml. So instead of having to unwind the stack when you encounter an exception, you just execute 2 instructions and go to the handler. The other convention is the C convention, and this comes into play when you invoke external C functions. So when you switch from OCaml into the C runtime, because all registers are caller saved, you don't need to spill any registers on the stack. And so switching into C is pretty fast. But in some cases, you want more control into which registers are spilled, and for that there is a special convention which is used by the bump allocator. So in the special convention, special routines like the bump allocator can tell the register allocator which registers it clobbers. So in that case, the compiler doesn't need to spill all live registers It only needs to spill the live register if it's clobbered by the special routine. A consequence of this is if the special routine breaks the contract, that is, it clobbers the register it said it wouldn't clobber, then you would need to spill and restore that on its own. So what do we do? Let's say we were to implement the primitives as external C functions, right? That may result in poor performance because we may be spilling registers we don't need. And since with Perceus, RC operations are called more frequently, we don't want to pay the cost of spilling and restoring, right? So in this example here, if RC-dup clobbers, say, a register R10, there's no need to spill RAX and RCX, right? So you could just do away with that and just call RC-dup and things will run fine, right? So what we need is a way to tell the register allocator which registers are clobbered by our primitives. And as I mentioned before, we can appeal to a special convention. So when implementing these primitives, we use a special convention and we tell the code generator that every RC primitive clobbers at most 2 fixed registers. We picked R10 and R11, but we could have picked anything else. In fact, OCaml sort of has R14 and R15 fixed as well. R15 points to the camel state. I actually forget which one points to which one, but they're fixed in the compiler. So we implement the fast paths of the primitives carefully in assembly, making sure we only clobber those 2 registers. In the case of dup, for example, my pointer, over here, notice that we don't clobber any registers, so there's no need to spill. But in the case of drop, which I've inlined there, we clobber R11. But now, for more complicated routines like recursive drop, we do want to switch into C because it's a little complicated to implement it entirely in assembly. So when we do happen to switch into C, we now need to spill the entire register state because we lied to the code generator and said we would only clobber R10 and R11, but we don't know which register C would clobber, so we need to spill everything and restore it. So we do the same thing for allocation as well, because we want fast allocation, since with RC primitives, they'll get invoked more often. So to do that, we use memalloc, which is a highly performant and scalable allocator used by Coca and Lean. The good thing about memalloc is that it has fast paths that we can inline. So here's an example of an inlined fast path. This is the free operation. So notice how it's very lean. In fact, the fast path, we can sort of run it in about 8 to 10 instructions. And those only include a single test instruction. Now, in case the fast path fails, we make the call into C using gcall over here, and it switches into the C runtime and invokes memalloc's generic free operation. So, as I mentioned before, if you use a special convention, there is a cost to it, in that when we switch into the C runtime now, it's a bit more expensive, but we only pay this for slow and infrequent paths, so the cost is sort of amortized. So that's the primitives part. So in summary, we've modified the OCaml compiler, and we no longer need the GC. We can turn it off completely. So the next question we need to answer is, how does it perform? Right? Will it perform well? So to do that, we evaluated the OCaml GC with 2 variants of Perceus. One that doesn't turn on any optimization, so Perceus as is, and the second one which turns on drop specialization. The benchmark suite is limited. It's the same as that of the Perceus paper. And here are the machine specs. So before we get to seeing the actual graph, I wanted to show how the assembly looks like now. So on the left is what the GC OCaml would generate. So note how it mainly includes program logic. There is only a very little bit towards the end which actually deals with the OCaml runtime. It first tries to allocate using the bump allocator, which is only about 3 instructions long. And then if that fails, it jumps and calls the GC towards the end. But with Perceus, we're executing way more code. So there's all these reference counting operations peppered throughout the assembly. And so if you look at this on the surface, it seems as though we're not looking too good, right? Because we're executing more code. But the results actually show that we're not doing that bad, actually. So here, orange is OCaml, Red is Perceus, and blue is Perceus with a drop specialization, and lower is better in these graphs. So note how we're doing pretty good in execution time, performing better than OCaml in a couple of the benchmarks, except RB3. Memory usage drops by half in C-fold and N-queens. C-fold performs constant folding over a large tree. Deriv performs a derivative over an expression tree. RB3 is RB3 insertion, and RB3CK is RB3 insertion with a shared spine. Another thing I wanted to highlight is drop specialization has a big impact on performance, as we can see in RB3. So the performance nearly improves by 2 times when we enable drop specialization for RB3, and that's because the reference counting operations are kind of expensive if we just do them naively. Another thing I did want to highlight is for 3 of the benchmarks, the memory usage of the GC and that of Perceus is about the same, which is a testament to how well engineered the OCaml GC is. It's quite impressive. Cool. So we had to tell this to ourselves quite a bit, actually. We don't want to get too excited because there's a long way to go. And so I just wanted to put that out there as well. In terms of future work, the benchmark suite is very limited. So we want to evaluate this on a bigger benchmark suite so that we have more confidence in how the system runs. We do want to implement reuse analysis because we feel like it will improve our performance in some of the benchmarks like RB3. One thing I did forget to mention is the benchmarks are representative of memory-intensive functional programs. So it's not entirely bad, but we still want to evaluate it on a bigger benchmark suite. And then finally, we do want to support like the entire OCaml language, so exceptions, mutable references, and multi-core OCaml. We did look into, we thought of starting with multi-core OCaml, like the whole implementation, but it wasn't officially announced yet, and we had trouble getting it to build, so we just went with 4.14 at the time. Yeah, so thank you for having me speak. Source code is available on GitHub. Thesis is available on my website, and we are looking for a student to help push the project forward, so help us with implementation and stuff. So if you're interested, come chat with us after the talk. Thank you.
So we have some time for the questions.
Thanks for that. So when you move over to multi-core or multi-threaded implementation, you're probably going to have to switch over your reference counts to atomic variables. And there's one operation in there in Perceus that was is unique,
Yes.
which doesn't seem like that'll translate at all. So what do you think the performance is going to do when you start introducing? Like, do you have any ideas of what the performance is going to be like once you start introducing?
Yeah, we actually do use atomic operations for reference counting. Like we have a condition that checks if we need to go into the atomic case. In terms of how bad it will perform, I'm not sure because we'll have to see. But maybe you have a better idea. Yeah.
It's a great question, by the way.
Yeah.
So this happens in Coca too. It's a nice. What we do in this implementation is it's like a positive reference count. We just don't use atomics. And when things could potentially be shared between threads, we have used negative reference counts. And then the test, then we do one test, then we switch to using an atomic operation. And it can only work if the language is static enough that you can detect when things can become potentially shared between threads. And it's the same how Lean does this, because it kind of requires this monotonicity of the reference count. So, yeah, I can show you. Yes, and there's tricks you can do.
Great. Simon Peyton-Jones. Just a couple of two sort of standard questions about reference counting. By the way, I really like this work. It's great to experiment with this. One is, what about cycles? And isn't reference counting incompatible with the efficient bump pointer allocation that you described? And the second question is, you showed just wall clock summaries, right? So some of that wall clock improvement comes from the fact that we don't have garbage collection. Balanced again, we do have more overheads during mutation. And I wonder whether you measured those separately. Like if you said, suppose GC was free, then what would the comparison look like?
Okay. Well, for the first question, which was about the bump allocation being incompatible with RC, well, that's why we use memalloc, because it does have a minor heap and like it has a minor heap and a major heap, and so it's sort of similar to the bump allocation, except that it uses more instructions. And what was the first part to the question? I forget. Oh, cycles. Yeah, cycles are a problem. So I guess the way they handle it in Coca is the programmer has to explicitly break the cycle. So yeah, so you
Don't handle cycles.
yeah.
Okay.
It's basically,
Okay.
Yeah.
so also, the bump allocator is not used in the
In this
Perceus
work, yeah.
He just showed it as an example for how the garbage collector is done. We just use memalloc, malloc and free.
Okay.
And what was the last one? Right, that is a great suggestion.
Measuring the overheads of garbage collector separately from the mutator.
Yes,
Yeah.
we have not done this, but it's a great suggestion. It works great on the baseline. And I think this is part of why we wanted to do this work, to get better insights in how what is really,
It's like a
how
limit
do they
set.
compare.
Yeah, so if GC was free, right, how much worse would Perceus be?
Yes,
Okay, thanks.
Hi, JJ, University of British Columbia. Really cool work. I was wondering. I was wondering with the zero garbage the zero garbage system that you have and doing the deallocations earlier. Do you lose any performance by doing these deallocations separately rather than if you have like a very large list with a lot of memory, doing them all at once at the end of scope? I mean, obviously you gain a bunch of more space in memory, but...
Right. So I think one thing that's neat about the bump allocated system is that it performs this optimization in which it coalesces memory in a pass, so it can like sort of allocate it in one chunk and deallocate it in chunks. But we don't do that in this system. And instead, what we do is like in the map example, if I can go back to it real quick. So what we're doing here is we are freeing the list as we traverse it. So there's no garbage at any point during execution, right? I don't know how much of an impact we would have if we just free the entire list at the end. I guess you would still have to iterate through the fields and free them, right? So I'm not sure. Yeah.
There is a benefit to cache locality by doing it right away. Suppose you have a really long list and you wait freeing it, and by the time you're at the end, you're going to free the list, you're going to trash your caches. But if you do it while you go at it, you win in the cache level. So sometimes I think maybe nowadays reference counting starts to work because it's so important to be cache local. But in the older days, it was too expensive to do the increments and decrements. One of my theories.
Do you have data to support that?
No data. I don't know, Simon. Right, yes. So yeah, to be clear about that, there's real research there, like understanding why it looks like this. We don't know.
Anil Madhuripati from Cambridge, lovely work. I'm curious about how you might ever have. This thing is randomly turns on and off. I'm curious about how you might ever handle exceptions and effects, because they're effectively just long jumps that just go somewhere else, and the garbage collector takes care of cleaning up the system afterwards. So, is there ever an efficient way where a reference counter could work with exceptions that remain fast, as in OCaml?
I think we would have to take a hit, right? Because we would need to. So Perceus depends on knowing the liveness of objects, right? And so the way it inserts reference counts is it looks at when like a particular value is live, and then it inserts it like when it knows it's no longer live. So I feel like we will take a hit on exceptions. So, but I was talking to someone else the other day, and like exceptions in OCaml, I don't think are used in the same way as they're used in, say, Python. Like when you iterate a list in Python, right, there is an exception that's thrown saying that, oh, we're at the end of an iteration. But in OCaml, I think exceptions are thrown in truly exceptional cases, right?
So exceptions are, they are used for control flow.
Right, oh, they are, okay.
But effects are they really have to be very fast because they interrupt that function.
Okay.
And they go back and forth.
Yeah.
But it's,
Yeah, I think we'll take a hit, yeah.
So you're claiming garbage freeness, but it seems that your definition of garbage is what is kind of live, what is live in the sense of, not in the sense of what the computation actually needs for the rest, or the program needs for the rest of the computation. It's more like what is really traceable through pointers. So that might. I mean, you might actually do better. You might have something in the closures that are not going to be accessed for the last call of the function, and you might actually be able to decrease the count on those. So maybe you can comment a little bit on that.
It's a very big question, but
In some form.
the question is, what does garbage free really mean? Maybe you can do a little better. For example, are you holding on to things that are in a closure that you may actually never use anymore, like for the last call? It's kind of based on what's live, means like what can be traced at any point. And it may not, it may actually, you could allocate some things, maybe even earlier. So garbage free is a very technical term, like how we prove it like according to calculus. And for things like closures, we actually, when you do the last call, we treat them as just like as with constructors. So we also drop as fast as possible. We don't leave something hanging in the closure. But you're right. There's a traceability aspect, right? It's like what you statically can see will be the last use of a variable. That's the time you drop. I think it would be very hard to do better than this. But you're also an expert, so maybe.
Well, okay. Well, that was the last question. Well, further discussion through Discord, please. And then, well, thank you again.
Thank you.